Hello, in this lecture we will find out the length of line segment X. In the drawing we have two quarter circles. The two quarter circles touch each other here at point B. In addition, we know that line segment AB equals to 1 unit in its length, and line segment QS equals to line segment SP, and our mission is to find out the length of this line segment BC that is equal to X. Okay, so in any quarter circle, this angle equals 9 degrees, and here in the big quarter circle, this angle equals 90 degrees, and we know that in the small quarter circle, PA equals to AB. They are both the radii of the quarter circle, therefore they are equal to each other. But AB equals to 1 according to what is given in the equation, therefore PA will be also equal to 1. Likewise, in the big quarter circle, BC equals to QC. They are both the radii of the quarter circle, therefore they are equal to each other. So BC equals to X, therefore QC must be also equal to X. Our mission is to find out the value of X, of the length of line segment BC. Okay. In the next step, we will join points P and B together by a straight line, and points Q and B together by a straight line. By joining points P and B, we created the right triangle PAB. So I will copy triangle PAB in a new page, and we will implement the Pythagoras theorem on this right triangle PAB. By PT is the evaluation for Pythagoras theorem. So actually, this is the right triangle PAB that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle PAB, PB squared, that is the square of the hypotenuse, equals to PA squared plus AB squared. We have already found out that PA equals to 1 and AB equals to 1. So I know that side PA equals to 1 and side AB also equals to 1. So in the right triangle PAB, PB squared equals to PA squared plus AB squared. So PB squared equals to PA squared. PA is 1, therefore PA squared is 1 squared, that is 1, plus AB squared. AB is also 1, therefore AB squared is 1 squared, that is 1. So in total, PB squared equals to 1 plus 1, that is 2. PB squared equals to 2. we take out of this equation, and we get that PB, the length of the hypotenuse PB, is equal to the square root of 2 units. So I can write down in the original drawing that PB equals to the square root of 2 units in its length. Likewise, I will copy the right triangle QCB in a new page, and we'll implement the Pythagoras theorem on this right triangle QCB. By PT is the permission for Pythagoras theorem. So this is the right triangle QCB that I copied from the original drawing. According to the Pythagoras theorem, this right triangle QCB, QB square, the square of the hypotenuse, equals to QC square plus BC square. So QB square equals to QC square. QC is x, therefore QC square is x square plus BC square. BC is also equals to x, so BC square is x square. So in total, QB square equals to x square plus x square, that is 2x square. QB square equals to 2x square. We take out of this equation, and we get that QB equals to the square root of 2x square. So QB equals to the square root of 2 times the square root of x square. The square root of x square is x. So in total, QB equals to the square root of 2 times x. The length of the hypotenuse QB is equals to the square root of 2 times x. So I write down in the original drawing. This is the hypotenuse QB of the right triangle QCB. It is equals to the square root of 2 times x units in its length. So, in both right triangles, the two perpendiculars are equal to each other. Okay? And we have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides, we have those two angles that must be also equal to each other. So if this angle is alpha, then this angle must be also equal to alpha, because they are equal to each other. Okay. The same rule is true here. In front of those two equal sides, we have equal angles. So those two angles must be also equal to each other. So if this angle is theta, then this angle must be also equal to theta. And we also have the rule that the sum of the angles in any triangle is equal to 180 degrees. So we'll focus on the right triangle PAB. On the right triangle PAB, the sum of the angles must be equal to 180 degrees. So which angles we have inside the right triangle PAB? We have theta plus theta is 2 theta plus 90 degrees. In total, they must be equal to 180 degrees according to the rule that I mentioned. Again, in the right triangle PAB, 2 theta plus 90 degrees equals to 180 degrees. We subtract 90 degrees from this equation, and we get that 2 theta equals to 180 degrees minus 90 degrees, it is 90 degrees. We divide this equation by 2, and finally we get that theta equals to 90 degrees over 2 is 45 degrees. So this angle equals to 45 degrees. And this angle also equals to 45 degrees. Likewise, in the right triangle QCB, the sum of the angles must be equal to 180 degrees. So 2 alpha plus 90 degrees equals to 180 degrees. And again, 2 alpha, the right triangle QCB, 2 alpha plus 90 degrees equals to 180 degrees. We subtract 90 degrees from this equation. We will get that 2 alpha equals to 90 degrees. We divide this equation by 2, and finally we get that alpha equals to 45 degrees. So this angle alpha equals to 45 degrees in its size, and this is angle alpha that is also equals to 45 degrees in its size. Okay. So here on top it again. Okay, so all the angles here are equal to 45 degrees. Okay. In the next step, I will present to you rule number 3, and we will implement rule number 3 in our drawing. According to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So in the drawing, we have the straight line AB. If we focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to this rule, rule number 3. So which angles we have at the upper side of AB at point Q? We have this angle alpha and angle beta. So in total, alpha plus beta must be equal to 180 degrees according to this rule, rule number 3. So we can actually implement rule number 3 in our drawing. Well, because if we focus on the upper side of the straight line AC, this is straight line AC, in the upper side of the straight line AC at point B, here the sum of the angles must be equal to 180 degrees according to rule number 3. So I copied the straight line AC in a new page with point B on it, and we implement rule number 3 on this straight line AC. So actually, this is the straight line AC. There's a curve from the original drawing. This is point B. So if you focus on the upper side of the straight line AC at point B, here the sum of the angles must be equal to 180 degrees according to rule number 3. So which angles we have at the upper side of AC at point B? We have this angle that is equal to 45 degrees plus the missing angle that we define as x plus this angle that is also equals to 45 degrees. In total, the sum of those three angles must be equal to 180 degrees according to rule number 3. 45 degrees plus 45 degrees is 90 degrees, so 90 degrees plus x equals to 180 degrees. We subtract 90 degrees from this equation. And we get that x equals to 180 degrees minus 90 degrees, it is 90 degrees. So the missing angle here equals to 90 degrees. Again, write down in the original drawing, this is the missing angle PBQ is the missing angle, and it is equals to 90 degrees in its size. It is a right angle. And therefore, triangle PBQ is a right triangle. So I will copy the right triangle PBQ in the new page, and we will block this right triangle PBQ by a circle. We have the rule that any triangle can be blocked by a circle, and especially the right triangle PBQ. So actually, this is the right triangle PBQ that I blocked by this circle, and we have a rule that relates to any. So here in the drawing we have peripheral angle PBQ, this peripheral angle PBQ, again, this peripheral angle PBQ is equals to 90 degrees in its size. And we have rule number 5 that relates to any peripheral angle that is a right angle. According to rule number 5, any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. So in the drawing we have a circle, inside this circle we have peripheral angle MAN. This peripheral angle MAN is a right angle, it is equal to 90 degrees in its size. And therefore, according to this rule number 5, this peripheral angle MAN must rest on the diameter of the circle. That is to say, MN is the diameter of the circle. It is very easy to see that MN is the diameter of the circle because MN, chord MN passes through point O, that is the center of the circle, and any chord that passes through the center of the circle must be the diameter of the circle. Therefore, peripheral angle MAN rests on the diameter of the circle, because MN is the diameter of the circle. Okay. So actually we can implement all number 5 in our drawing. Why? Because in our drawing we have peripheral angle MAN equals to 90 degrees in its size, is a right angle, and therefore according to rule number 5, PQ is the diameter of the circle. PQ is the diameter of the circle. Chord PQ is the diameter of the circle. If we define the radius of this circle as R, then the diameter PQ must be equal to 2R. Okay. If we want to find out that PQ equals to 2R, that is from one side, but from the other side, we have this is PQ, and according to what is given us in the question, PS equals to SQ. So if PS is X, then SQ must be also equal to X because they are equal to each other. Okay, so the length of PQ equals to PS plus SQ. That is to say PQ equals to PS, that is X, plus SQ, that is X. So in total, PQ equals to X plus X, that is to X. So from one side, we found out that PQ equals to 2R, it is the diameter of this circle. From the other side, PQ equals to 2X. And from those two equations, we derive that 2R equals to 2X. We divide this equation by 2, and finally we get that R equals to X. R equals to X. So we can write here that X equals to R, and then also X equals to R. In the next step, I will copy point S that is located on PQ to the new drawing here. So I'll copy point S from the original drawing to our new drawing, because point S is located on PQ. I'll copy point S from the original drawing to the new drawing here. So actually, this is point S that I copied from the original drawing exactly to the same location on PQ. That is, it was in the original drawing. And we already found out that PS is R, PS equals to R, SQ also equals to R, SQ also equals to R. So, in the drawing we have those two radii of this circle touch each other at point S, because this radius starts from point P and ends at point S. This radius also starts from point Q and ends at point S. So those two radii touch each other at point S. Therefore, point S is the center of the circle. So I can write down here that point S is the center of the circle. Because the center of a circle is the point where all the radii touch each other. So point S is the center of the circle. In the next step, we will join points S and B together by a straight line. So point S is the center of the circle, point B is the point of the circle itself, therefore SB is the radius of this circle that is equal to R. So in conclusion, we found out that PS equals to SQ equals to SB. They are all the radii of this circle, therefore they are equal to each other. So we join points S and B in the original drawing. SB is the radius of the previous circle, so it is equals to R. And here again, PS equals to SB equals to SQ, and especially SB equals to SQ. Okay. In the next step, I will copy the quarter circle to a new page, and we will complete this quarter circle, the big quarter circle, to a circle. Okay. So actually, this is the big quarter circle that I copied from the original drawing. In the next step, I will complete this quarter circle to a circle. So I completed the quarter circle to a circle. In the drawing we have SB equals to SQ. They are both the radii of the previous circle, therefore they are equal to each other. So in the next step I will present to you a new rule and we'll implement the new rule in our drawing. The new rule is rule number 13. According to rule number 13, a central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have a circle. Inside this circle we have peripheral angle ACB. This peripheral angle ACB equals to theta in its size, and it rests, so it's subtended on RKB. Again, peripheral angle ACB is subtended on RKB. In addition, in the drawing we have central angle AOB. This central angle AOB is subtended on the same arc AB. And because of the fact that the peripheral angle is subtended on the same arc, the central angle is subtended on the same arc as this peripheral angle. Therefore, the central angle must be twice as large as this peripheral angle. This is according to rule number 13. And because of the fact that peripheral angle ACB, this peripheral angle ACB equals to theta, then the central angle AOB that is subtended on the same arc RKB will be equal to 2 theta. It is twice as large as the peripheral angle that is subtended on the same arc RKB. Okay, so we can actually implement rule number 13 in our drawing. Why? Because in our drawing we have the peripheral angle BSQ. This peripheral angle BSQ is subtended on arc QB, on the big arc RQB. And the central angle QCB, this is the central angle QCB, the central angle QCB is subtended on the same arc QB. And because of the fact that the central angle is subtended on the same arc as this peripheral angle, the central angle must be twice as large as this peripheral angle. This is according to rule number 13. So in the next step, we'll find out the size of the central angle QCB, the size of this angle. According to a new rule, that is rule number 6. According to rule number 6, the sum of the angles around a point will always add up to 360 degrees. So in the drawing we have, this is point A, and according to rule number 6, this rule number 6, the sum of the angles around point A must be equal to 360 degrees. Okay, in order to prove that this rule is true, I drew this straight line that passes through point A. Now we can use here rule number 3. According to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on the upper side of this straight line at point A, here the sum of the angles must be equal to 180 degrees. Likewise, if we focus on the lower side of this straight line at point A, here the sum of the angles also must be equal to 180 degrees. According to the same rule, rule number 3. So in total, the sum of the angles in the upper side plus the sum of the angles in the lower side of this straight line at point A will be equal to 180 degrees plus 180 degrees, that is 360 degrees, exactly according to this rule. It says that the sum of the angles around point A is equal to 360 degrees. Okay, now we can implement rule number 6 in our drawing. Why? Because in our drawing, if you focus at point C, this is point C. Here, the sum of the angles around point C in total must be equal to 360 degrees according to rule number 6. So which angles we have at around point C? We have this angle that's equal to 90 degrees plus this missing angle. In total, the sum of those two angles must be equal to 360 degrees, again according to rule number 6. Therefore, the missing angle here must be equal to 270 degrees. Why? Because 90 degrees, this angle is a right angle that is equal to 90 degrees plus the missing angle that is 270 degrees. In total, they are equal to 360 degrees, exactly according to rule number 6 that says that the sum of the angles around point C must be equal to 360 degrees. So, angle QCB, the central angle QCB equals to 270 degrees in its size. And therefore, peripheral angle BSQ that is subtended on the same arc RQB must be equal to half of it. That is to say, it must be equal to 270 degrees over 2, that is 135 degrees. Okay. In the next step, we will focus on triangle QSB. Triangle QSB is an isosceles triangle. Why? Because side SB equals to side SQ. They are both the radii of the previous circle, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other. So if this is angle alpha, then this angle must be also equal to alpha, because those two angles are equal to each other because they are located in front of equal sides. Okay, and we also know that the sum of the angles in any triangle is equal to 180 degrees. And especially it is true in the isosceles triangle, triangle SQB, or SPQ, it is the same. So in the right triangle SQB, the sum of the angles must be equal to 180 degrees. So which angles we have inside the isosceles triangle SQB? We have this angle alpha, this is also angle alpha, so alpha plus alpha is 2 alpha. 2 alpha plus this angle is 135 degrees. In total, they must be equal to 180 degrees according to the rule that I mentioned. Here we subtract 155 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 135 degrees is 45 degrees. We divide this equation by 2, and finally we get that alpha equals to 45 over 2 degrees. So this is angle alpha, angle SQB is alpha, that is equal to 45 over 2 degrees, and this is also angle alpha, that is equal to 45 over 2 degrees. Okay, so in the next step, I will copy the right triangle PBQ in a new page, and we'll analyze this right triangle, triangle PBQ. We have already found out that side PB equals to the square root of 2 units in the beginning of the lecture, and side QB equals to the square root of 2 times x units. this is angle alpha, this angle SQB. We have already found out that angle SQB, this is angle SQB, this is equal to alpha, and alpha equals to 45 over 2 degrees. So this angle alpha is equals to 45 over 2 degrees in its size. So this is angle alpha, this is equals to 45 over 2 degrees. So this is the right angle QPB that I copied from the original drawing. In this right triangle QBP, tangents 45 over 2 degrees, tangents 45 over 2 degrees equals to PB over QB. So tangents 45 over 2 degrees, the tangents of this angle that is 45 over 2 degrees equals to PB. PB is square root of 2 over QB. QB is square root of 2 times x. So we have square root of 2 in the numerator and square root of 2 in the denominator, so square root of 2 will get cancelled. And we're left only with 1 over x. In conclusion, we found out that tangents 45 over 2 degrees equals to 1 over x. This is equation number 1. I repeat again. We found out that according to equation number 1, tangents 45 over 2 degrees equals to 1 over x. But we also have the trigonometric identity that states that tangents 2 theta equals to 2 tangents theta over 1 minus tangents square theta. Repeat again, according to this trigonometric identity, tangents 2 theta equals to 2 tangents theta over 1 minus tangents square theta. In the next step, we will define theta as 45 over 2 degrees. If theta is 45 over 2 degrees, it means that 2 theta is 45 degrees. Okay? And we will substitute theta in this trigonometric identity by 45 over 2 degrees, and we substitute 2 theta by 45 degrees. And we get that, so this will be equation number 2. According to this trigonometric identity, we have tangents 2 theta, and 2 theta according to our definition is 45 degrees. And it is equals to 2 times tangents theta, and theta according to our definition is 45 over 2 degrees over 1 minus tangents square theta, and theta according to our definition is 45 over 2 degrees. So in conclusion, we found out that according to equation number 2, tangents 45 degrees equals to 2 times tangents 45 over 2 degrees over 1 minus tangent square 45 over 2 degrees. Tangents 45 degrees is 1, and it is equals to 2 times tangents 45 over 2 degrees. We will define tangents 45 over 2 degrees as t, and we'll substitute tangents 45 degrees over 2. We'll substitute tangents 45 over 2 degrees in this equation number 2 by t. So in equation number 2 we have times 45 degrees is 1, and it is equals to 2 times 45 over 2 degrees. And according to our definition, times 45 over 2 degrees is t. So we substitute it by t. So in total, in the numerator we have 2t over, in the denominator we have 1 minus tangent square of 45 over 2 degrees. If tangent 45 over 2 degrees is t, then it means that tangent square of 45 over 2 degrees will be equal to t square. So in total, in the denominator we have 1 minus t square. So found out that according to equation number 2, 1 equals to 2t over 1 minus t square. Here we will multiply this equation number 2 by 1 minus t square, and we get that according to equation number 2, 1 minus t square equals to 2t. Here we will add to this equation number 2 t square, and we get that according to equation number 2, 1 equals to t square plus 2t. Here we subtract 1 from this equation number 2, and finally we get that according to equation number 2, t square plus 2t minus 1 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, t squared plus 2t minus 1 equals to 0, the variable that we are looking for is t. So x equals to t. So the coefficient a is 1, equals to 1. The coefficient b equals to 2. And finally, the coefficient c equals to minus 1. Now we put the data inside the formula for x, and we will find out the value of the values of t. Why? Because the variable that we are looking for in our quadratic equation is t, so x equals to t. So here x equals to t, so we substitute x by t, and t equals to minus b. b is 2, therefore minus b is minus 2, plus minus square root of b squared. b is 2, so b squared is 2 squared, that is 4, minus 4 times a is 1, times c, that is minus 1, all divided by 2 times a, and a is 1, so it is 2 times 1. So in conclusion, we actually found out that t equals to minus 2 plus minus, so, and inside the root we have minus 4 times minus 1 is plus 4, and 4 plus 4 is 8. So in total, in the root we left only with 8 over 2. So we actually found out that t equals to minus 2 plus minus square root of 8. And 8 is 4 times 2, so we'll substitute 8 by 4 times 2 over 2. So actually found out that t equals to minus 2 plus minus square root of 2 is 2, so inside the root we left only with 2 divided by 2. T equals to minus 2 plus minus 2 times square root of 2 over 2. So t equals to minus 2 over 2 is minus 1 plus minus square root of 2 over 2 is 1, so this expression in total equals to the square root of 2. In conclusion, found out that t equals to minus 1 plus minus square root of 2. So here we will have two solutions that are possible for t. The first solution for t is that t equals to minus 1 minus square root of 2, and the second solution for t is t equals to minus 1 plus square root of 2. So according to the first solution for t, according to the first solution for t equals to minus 1 minus square root of 2. Minus 1 minus square root of 2, it is a negative number, therefore t is a negative number. But according to our definition, t equals to tangents 45 over 2 degrees, that is a positive number. Therefore t is a positive number. A positive number can never be equal to a negative number. We have a contradiction. T cannot be simultaneously a negative number and a positive number. Therefore we have a contradiction here. Therefore we cancel this solution. And we left only with the second solution that is possible for t. T equals to minus 2 plus square root of 2. And according to our definition, t equals to tangents 45 over 2 degrees. So actually we found out that this will be equation number 2. Tangents 45 over 2 degrees equals to t, and t equals to minus 2. T equals to the square root of 2 minus 1 according to the second solution for t. So in conclusion, found out that according to equation number 2, tangents 45 over 2 degrees equals to the square root of 2 minus 1. While according to equation number 1, we have already found out that tangents 45 over 2 degrees equals to 1 over x. I'll show you that we found it here. We actually found a couple of minutes ago that tangents 45 over 2 degrees equals to 1 over x. This is according to equation number 1. While according to equation number 2, we just right now found out that tangents 45 over 2 degrees equals to the square root of 2 minus 1. Therefore, we'll create here equation number 3. We have two different expressions or two different equations for the value of tangents 45 over 2 degrees. Therefore, we create equation number 3 that states that tangents 45 over 2 degrees according to equation number 1 must be equal to tangents 45 over 2 degrees according to equation number 2. Tangents 45 over 2 degrees according to equation number 1 is 1 over x, and it must be equal to tangents 45 over 2 degrees according to equation number 2, that is square root of 2 minus 1. So in conclusion, we found out that according to equation number 3, 1 over x equals to the square root of 2 minus 1. Here we will multiply this equation number 3 by x, and we get that 1 equals to square root of 2 minus 1 times x. Here we divide this equation number 3 by square root of 2 minus 1, and we get that according to equation number 3, x equals to 1 over square root of 2 minus 1. Okay, so here we focus on this side of the equation, and we multiply this side of the equation by square root of 2 plus 1, and then we divide it by square root of 2 plus 1. Square root of 2 plus 1 over square root of 2 plus 1 is 1. And it is allowable to multiply anything by 1. Therefore, the operation is allowable. And we get that x equals to 1 over square root of 2 minus 1. Repeat again. We found out that x equals to 1 over square root of 2 minus 1. Now we multiply this side of the equation by square root of 2 plus 1, and then we will divide it by square root of 2 plus 1. So, and we get that x equals to, in the numerator we have square root of 2 plus 1 over square root of 2 minus 1 times square root of 2 plus 1. This expression is equals to, according to the following trigonometric identity, a minus b times a plus b is equals to a squared minus b squared. So according to this algebraic identity, a minus b times a plus b equals to a squared minus b squared, we will get that this expression, square root of 2 minus 1 times square root of 2 plus 1, will be equal to square root of 2 squared, that is 2, minus 1 squared, that is 1. So in total, this expression equals to 2 minus 1, that is 1. So we got here, in the numerator we have square root of 2 plus 1 over 1, that is actually square root of 2 plus 1. In conclusion, we found out that x equals to either square root of 2 plus 1 units, or in terms of numbers, x equals to 2.414 units. And that is the answer to the question. I'll repeat again. We actually found out that BC, that is equal to x, equals to either square root of 2 plus 1 units, or in terms of numbers, BC that is equal to x equals to 2.414 units. Okay, so in the next step, I will summarize the lecture. In this lecture, we found out the length of this line segment BC, is equal to x. So in the drawing we have two quarter circles. Those two quarter circles start each other here at point B. In addition, we know that AB, line segment AB equals to 1 unit in its length. We also know that QS equals to SP. Again, our mission is to find out the length of this line segment BC that is equal to X. Okay. So first of all, in these small quarter circles, PA equals to AB, they are both the radii of this quarter circle, therefore they are equal to each other. But it is given as the equation that AB equals to 1, therefore PA must be also equal to 1. Likewise, in the big quarter circle, according to what is given as the equation, BC equals to X. That is what we are looking for, to find out the length of BC is equal to X. Therefore, QC, that is also the radius of this quarter circle, must be also equal to X. Okay. Then I copied the right in any quarter circle. Those two angles, they will be always right angles. They are equal to 90 degrees. So in the next step, I copied the right triangle PAB in a new page and implemented the Pythagoras theorem in this right triangle PAB. This is the right triangle PAB that I copied from the original drawing. In this right triangle PAB, PB square equals to PA square plus AB square. So PB square equals to PA square. PA is 1, therefore PA square is 1 square, that is 1, plus AB square. AB is 1, therefore AB square is 1. So in total PB square equals to 1 plus 1, that is 2. PB square equals to 2. We took out of this equation and finally found out that PB equals to the square root of 2 units. Here, the hypotenuse PB of the right triangle PAB equals to the square root of 2 units in its length. Then I copied the right triangle QCB here in the new page and we implemented the Pythagoras theorem in this right triangle QCB. This is the right triangle QCB that I copied from the original drawing. In this right triangle QCB, QB square equals to QC square plus BC square. So QB square, that is the square of the hypotenuse, equals to QC square. QC is X, therefore QC square is X square plus BC square. BC is X, therefore BC square is X square. So in total, QB square equals to X square plus X square, that is 2X square. QB square equals to 2X square. We took out of this equation and finally found out that QB equals to the square root of 2 times X square. The square root of 2 times X square equals to the square root of 2 times the square root of X square is X. So in total, QB equals to the square root of 2 times X. Here, QB, the hypotenuse QB of the right triangle QBC equals to the square root of 2 times X units in its length. Okay, then we have here those two right triangles are also an isosceles triangles. Why? Because here PA equals to AB. In this right triangle, QC equals to BC. Therefore, we have here two right triangles that are also isosceles triangles. And here we know that PA equals to AB. So those two sides are equal to each other. And we have the rule, and here also QC equals to BC. In both right triangles, we can implement the rule that in front of equal sides in the triangle, there are equal angles. So in front of those two sides, we have those two angles that are equal to each other. So if this angle is alpha, this angle must be also equal to alpha. Okay. Likewise, in front of those two equal sides, we have those two angles that are equal to each other. So if this angle is theta, then the other angle must be also equal to theta because they are equal to each other. And we also know that some of the angles in the right triangle QCB must be equal to 180 degrees. That is to say, theta plus 90 degrees equals to 180 degrees. Repeat again, the right triangle QCB theta plus theta, that is 2 theta plus 90 degrees equals to 180 degrees. We subtracted 90 degrees from this equation and finally found out that 2 theta equals to 180 degrees minus 90 degrees is 90 degrees. We divided this equation by 2 and finally found out that theta equals to 45 degrees. This is angle theta that is equal to 45 degrees, this is angle theta also equals to 45 degrees. Likewise, in the right angle PAB, in front of those two sides, we have those two angles that are equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha. And we also know that the sum of the angles in the right angle PAB equals to 180 degrees. That is to say, alpha plus alpha, that is 2 alpha, plus 90 degrees equals to 180 degrees. I repeat again. In the right triangle PAB, alpha plus so it can be alpha or theta, it doesn't matter. So theta plus theta is 2 theta plus 90 degrees equals to 180 degrees. We subtracted 90 degrees from this equation and finally found out that 2 theta equals to 180 degrees minus 90 degrees is 90 degrees. So 2 theta equals to 90 degrees, we divided this equation by 2 and finally found out that theta equals to 45 degrees. So this is angle theta is equal to 45 degrees and this angle theta equals to 45 degrees. Then I presented to you rule number 3 and we implemented rule number 3 in our drawing. According to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So here in the drawing we have the straight line AB. If you focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees. According to this rule number 3. So which angles we have at the upper side of AB? At point Q we have this angle alpha and beta. So in total alpha plus beta must be equal to 180 degrees. We can actually implement rule number 3 in our drawing, because in our drawing, if we focus on the upper side of this straight line AC at point B, here the sum of the angles must be equal to 180 degrees according to rule number 3. So I copied the straight line AC in a new page and implemented here rule number 3. This is the straight line AC that I copied from the original drawing. This is point B. So if you focus on the upper side of AC at point B, the sum of the angles must be equal to 180 degrees according to rule number 3. So which angles we have at the upper side of AC at point B? We have this angle that is 45 degrees plus the missing angle that we define as x plus this angle that is 45 degrees. In total the sum of those three angles must be equal to 180 degrees. So here 45 degrees plus 45 degrees is 90 degrees. So in total in this side of the equation we have 90 degrees plus x equals to 180 degrees. If subtracted 90 degrees from this equation, we finally found out that x equals to 180 degrees minus 90 degrees is 90 degrees. So the missing angle here equals to 90 degrees. This is the missing angle PBQ is the missing angle, that is equal to x, and x equals to 90 degrees. So this angle equals to 90 degrees, it is a right angle. Then I copied the right triangle PBQ in a new page, and we blocked this right triangle PBQ by a circle. We have the rule that any triangle can be blocked by a circle. So this is the right triangle PBQ that is blocked by this circle. So in the drawing we have peripheral angle PBQ. This peripheral angle PBQ is a right angle, it is equal to 90 degrees in its size, and we have rule number 5 that relates to any peripheral angle that is a right angle. According to rule number 5, any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. So in the drawing we have this circle, inside this circle we have peripheral angle MAN. This peripheral angle MAN equals to 90 degrees in its size. Therefore, according to this rule number 5, peripheral angle MAN must rest on the diameter of the circle, that is to say, MN is the diameter of the circle. We can implement rule number 5 in our drawing. Because in our drawing we have this peripheral angle PBQ that is equal to 90 degrees in its size. Therefore, according to rule number 5, peripheral angle PBQ must rest on the diameter of the circle. That is to say, PQ is the diameter of the circle. PQ is the diameter of this circle. If we define the radius of this circle as r, then the diameter PQ must be equal to 2r. This is from one side. But from the other side, we have here PQ, and it is given us an equation that QS equals to SP. Here, QS equals to SP. So if QS is X, then PS equals to X also, because they are equal to each other. So what is the length of QP? The length of line segment QP in total will be equal to QS, that is X, plus SP, that is also X. That is to say, QP equals to X plus X, that is 2X. So from one side, QP equals to 2X, or PQ equals to 2X. From the other side, PQ is the diameter of the circle, is equal to 2R. From those two equations, we derive that 2R equals to 2X. We divided this equation by 2 and finally found out that R equals to X. R equals to X, here X, R equals to X, and here also PS, that is X, it is equals to R. Then I copied this point S that is located on PQ to the new drawing here. I copied this point S exactly where it is located on PQ here in the new drawing. This is point S that I copied from the original drawing on PQ. And we have already found out that PS equals to R and SQ also equals to R. SQ equals to R. So QS is the radius of this circle. It starts from point Q and ends at point S. PS is also the radius of this circle that starts from point P and ends at point S. That is to say, at point S, the two radii touch each other, and therefore point S is the center of this circle. Point S is the center of this circle. Then we join points S and B together by set line. Point S is the center of the circle, point B is the point on the circle itself, therefore SB is the radius of this circle, that is R. So in conclusion, we found out that PS equals to SB equals to SQ, they are all the radii of this circle, therefore they are equal to each other. In the original drawing also, we join points S and B. SB is the radius of the previous circle, is equal to R. Again, PS equals to SB equals to SQ, they are all the radii of the previous circle, therefore they are equal to each other. Then I copied this quarter circle to a new page, and after I copied it to a new page, we completed this quarter circle to a circle. This is the quarter circle that I copied from the original drawing, the big quarter circle. Here we already found out that SQ equals to SB. They are both the radii of the previous circle, therefore they are equal to each other. And this angle equals to 90 degrees because this is a quarter circle, therefore this angle equals to 90 degrees. Then I completed this quarter circle to a circle, and then I presented to you rule number 13 and implemented rule number 13 in our drawing. According to rule number 13, a central angle is twice as large as the peripheral angle subtended on the same arc. So we have here, this is a circle. Inside this circle we have peripheral angle ACB. This peripheral angle ACB equals to theta in size, and this peripheral angle ACB is subtended on RKB. Likewise, we have here central angle AOB. This central angle AOB is subtended on the same arc RKB. So the central angle and the peripheral angle in this drawing, they are both subtended on the same arc RKB. Therefore, according to this rule number 13, the central angle AOB must be twice as large as this peripheral angle ACB, because they are both subtended on the same arc RKB. So peripheral angle ACB equals to theta, therefore the central angle AOB must be equal to 2 theta. We can actually implement rule number 13 in our drawing. Why? Because in our drawing we have this peripheral angle BSQ. This peripheral angle BSQ, this is the peripheral angle BSQ that is subtended on RQB. QC, arc QB. This is arc QB. Okay, and we have center angle QCB. This is center angle QCB. This angle is subtended on the same arc, arc QB. Therefore, according to rule number 13, the center angle QCB must be twice as large as this peripheral angle QSB that is subtended on the same arc, arc QB. Now we have to find out the size of the center angle QCB, the size of this angle. In order to find out the size of this angle, of the center angle QCB, I presented to you rule number 6. According to rule number 6, the sum of the angles on one side of a straight line, the sum of the angles around a point will always add up to 360 degrees. So in the drawing we have this point A, and according to this rule number 6, the sum of the angles around this point A, must be equal to 360 degrees. In order to prove that this rule is true, I drew a straight line that passes for point A. Now we can implement here rule number 3. According to rule number 3, the sum of the angles on one side of the straight line is equal to 180 degrees. So the sum of the angles in the upper side of this straight line at point A must be equal to 180 degrees. Likewise, the sum of the angles in the lower side of this straight line at point A must be also equal to 180 degrees. So in total, the sum of the angles in the upper side of this straight line at point A plus the sum of the angles in the lower side of this straight line at point A must be equal to 180 degrees plus 180 degrees, that is 360 degrees. Exactly according to this rule that states that the sum of the angles around point A must be equal to 360 degrees. We can implement rule number 6 in our drawing. If we focus at point C, according to rule number 6, the sum of the angles around point C must be equal to 360 degrees. So which angles we have around point C? We have this angle that is a right angle. Therefore, the missing angle here must be equal to 270 degrees. Why? Because 270 degrees plus 90 degrees, it is 360 degrees, exactly according to rule number 6. That states that the sum of the angles around point C must be equal to 360 degrees. So the missing angle here equals to 270 degrees in size. That is to say, the size of the center angle QCB equals to 270 degrees, and therefore the size of the peripheral angle BSQ that is subtended on the same arc QB must be equal to 270 degrees over 2, that is 135 degrees. So this angle equals to 135 degrees in its size, and we have already found out that SB equals to SQ. They are both the radii of the perimeter circle, therefore they are equal to each other. And we have the rule, so those two sides are equal to each other. We focus on the isosceles triangle SBQ, and the isosceles triangle SBQ, in front of those two equal sides, there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. And we also know that the sum of the angles in any triangle, and especially in triangle QSB, must be equal to 180 degrees. So which angles we have inside triangle QSB? We have this angle alpha plus alpha, so alpha plus alpha is 2 alpha, plus 135 degrees. In total, they must be equal to 180 degrees. We subtracted 135 degrees from this equation, and finally found out that 2 alpha equals to 180 minus 180 degrees minus 135 degrees is 45 degrees, so 2 alpha equals to 45 degrees. We divided this equation by 2 and finally found out that alpha equals to 45 over 2 degrees. So this is angle alpha that is equal to 45 over 2 degrees, and this is also angle alpha that is equal to 45 over 2 degrees. Then I copied the right triangle PBQ in a new page, and we analyze this right triangle, triangle PBQ. This is the right triangle PBQ that I copied from the original drawing. PB equals to the square root of 2, QB equals to the square root of 2 times x, according to what we have already found out in the beginning of the lecture. And this is actually angle alpha is equal to 45 over 2 degrees. So in this right triangle PBQ, tangent 45 over 2 degrees equals to PB over BQ. Tangent 45 over 2 degrees equals to PB over BQ. PB is square root of 2, bq is square root of 2 times x. So we have square root of 2 in the numerator and square root of 2 in the denominator, so square root of 2 will get cancelled, and we left only with 1 over x. So in conclusion, we found out that according to equation number 1, tan 45 over 2 degrees equals to 1 over x. Okay, tan 45 over 2 degrees equals to 1 over x. This is according to equation number 2. While according to equation number, while we have actually the trigonometric identity that states that tangent 2 theta equals to 2 tangent theta over 1 minus tangent square theta. Okay, now we defined angle theta is 45 over 2 degrees. If theta is 45 over 2 degrees, it means that 2 theta is 45 degrees. In the next step, we substitute 2 theta by 45 degrees, and we substitute theta by 45 over 2 degrees in this trigonometric identity, and found out that according to this trigonometric identity, we have tangents 2 theta, 2 theta is 45 degrees, that equals to 2 tangents theta, theta is 45 over 2 degrees, over 1 minus tangent square theta, and theta is 45 over 2 degrees. So in conclusion, we found out that according to equation number 2, tangent 45 degrees equals to 2 times 45 over 2 degrees over 1 minus square 45 over 2 degrees. Then we defined tangent 45 over 2 degrees as t, and we substituted tangent 45 over 2 degrees in this, the equation number 2 by t. And we found out that according to this equation number 2, tangent 45 degrees is 1, and it is equals to 2 times, and times 45 over 2 degrees is t. So it is, the denominator we have 2t over 1 minus tangent square 45 over 2 degrees. If tangent 45 over 2 degrees is t, then tangent square 45 over 2 degrees is t square. So in total, the denominator we have here 1 minus t square. So if I found out that 1 equals to 2t over 1 minus t square, we multiply this equation by 1 minus t square, and we found out that 1 minus t square equals to 2t. Then we added t square to this equation and found out that 1 equals to t square plus 2t. We subtracted 1 from this equation and finally found out that t square plus 2t minus 1 equals to 0. This is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the variable that we are looking for is t, therefore x equals to t. X equals to t, the coefficient a equals to 1, the coefficient b equals to 2, and the coefficient c equals to minus 1. Then we put the data inside this formula in order to find out the value of the values of t, because x equals to t. So x equals to t, we substitute x by t. T equals to minus b, b is 2, therefore minus b is minus 2, plus minus square root of b squared. B is 2, so b squared is 2 squared, that is 4, minus 4 times a is 1, times c, that is minus 1, over 2 times a is 1, so it is 2 times 1. So inside the root we have minus 4 times minus 1 is 4, and 4 plus 4 is 8. So in total, in the root we left only with 8. So t equals to minus 2 plus minus square root of 8 over 2. Then we substitute 8 by 2, we substitute 8 by 4 times 2. Therefore we have here t equals to minus 2 plus minus square root of 4 times 2 over 2. The square root of 4 is 2, so inside the root we left only with 2 divided by 2. So t equals to minus 2 plus minus 2 times square root of 2 over 2. Minus 2 over 2 is minus 1, plus minus 2 over 2 is 1, so this expression in total equals to the square root of 2. So in conclusion, we found out that t equals to minus 1 plus minus square root of 2. So here we have two solutions that are possible for t. The first solution for t is that t equals to minus 1 minus square root of 2. And the second solution that is possible for t, that t equals to minus 1 plus square root of 2. So according to the first solution, t equals to minus 1 minus square root of 2. Minus 1 minus square root of 2 is a negative number. But according to our definition, t also equals to tangent 45 over 2 degrees, that is a positive number. So t cannot be simultaneously a positive number and a negative number. So we got to a contradiction. Therefore, we can set this solution, and we have to leave the second solution that is possible for t, that t equals to minus 2 plus square root of 2. But according to our definition, t also equals to tangent 45 over 2 degrees. So here we created the equation number 2 that states that tangent 45 over 2 degrees, that is t, equals to t that is also minus 2, t is also minus 2 plus square root of 2. This is according to equation number 2, while according to equation number 1, we have already found out that tangent 45 over 2 degrees is 1 over x. Then we created equation number 3 that states that tangent 45 over 2 degrees according to equation number 1 must be equal to tangent 45 over 2 degrees according to equation number 2. Tangent 45 over 2 degrees according to equation number 1 is 1 over x. It must be equal to tangent 45 over 2 degrees according to equation number 2, that is square root of 2 minus 1. So in conclusion, we found out that 1 over x equals to square root of 2 minus 1. We multiply this equation by x, and we found out that 1 equals to the square root of 2 minus 1 times x. Then we divided this equation number 3 by square root of 2 minus 1, and finally found out that x equals to 1 over square root of 2 minus 1. So x equals to 1 over square root of 2 minus 1. Then we multiplied this side of the equation by square root of 2 plus 1, and then we divided by square root of 2 plus 1. That is to say, we multiplied it by 1, therefore this operation is allowable. So here we multiplied this expression by square root of 2 plus 1, and then we divided by square root of 2 plus 1. So in the numerator we have square root of 2 plus 1, over in the denominator we have square root of 2 minus 1 times square root of 2 plus 1. This expression, according to the algebraic identity that a minus b times a plus b equals to a squared minus b squared, this expression will be equal to the square root of 2 squared, that is 2, minus 1 squared, that is 1. So in total, this expression equals to 2 minus 1, that is 1. So x equals to the square root of 2 plus 1 over 1. Square root of 2 plus 1 over 1 is square root of 2 plus 1. In conclusion, found out that x equals to either square root of 2 plus 1 units in itself, or in terms of numbers, x equals to 2.414 units. I repeat again, we actually found out that the length of this line segment BC is equal to x equals to either square root of 2 plus 1 units in itself, or BC is equal to x. In terms of numbers, it is equals to 2.414 units. Okay, thank you very much.